Good evening, everyone, and welcome to our latest episode of Physics Talk. Today, we talk about opportunities in the field of experimental particle physics, and we are talking with Mr. Malinda Shiram De Silva. But first, before we get to the meat of today's meeting, I'd like to formally welcome you all gathered here today. And for this, I'd like to invite the Secretary of the Physics Society of the University of Colombo, Mr. Rishi Ranchikliye. Rish, the screen is yours.
Thank you, Udita. Respected lecturers, our guest of honor, Mr. Malinda Shiram De Silva, President and Committee members of Physics Society, University of Colombo, and all the participants. Good evening to you all. I am Rishi Ranchikliye, and as the Secretary of the Physics Society, I would like to welcome you all to the session of Physics Talk on exciting new opportunities in the field of experimental particle physics. First of all, I would like to welcome you all to this session. And first of all, I would like to welcome our guest of honor today, Mr. Malinda Shiram De Silva. He is a former president of the Physics Society and a graduate in engineering physics from University of Colombo. And he is currently completing his Ph.D. in experimental physics at the University of Heidelberg, Germany. Next, I would like to welcome Professor Balu Daya, the senior professor, the senior treasurer of the Physics Society, along with all the lecturers and demonstrators who took time off their busy schedule to be with us here today. Then I would like to welcome Mr. Iran Kavinda, President of the Physics Society, along with all the committee members. Finally, I would like to welcome all the participants who have joined us here today. As the Physics Society of the University of Colombo, we are planning to do a series of physics talks starting from today, and we expect that you all will stay with us throughout this journey. We hope that we will be able to excite at least a few of young minds into thinking about a career in the field of physics. Welcoming you all once again, I would like to call upon Udita to carry out the rest of the session from here. Thank you.
Thank you, Rish. And yes, just like Rish mentioned, our guest today is Mr. Malinda Shiram De Silva. And he is a former student of the University of Colombo, and he was a former president of the Physics Society of the University of Colombo. He's a graduate from the University of Colombo, where he studied a special degree in engineering physics, which he completed in 2017. He also completed his master's in applied engineering in just this February 2020. And this he did at the Technical University of Munich. He is currently reading for his Ph.D. at the University of Heidelberg in Germany. And it's my honor and my privilege to invite our guest, Mr. Malinda, onto the screen. Guten Tag and willkommen zurück to the University of Colombo, Mr. Malinda. How's life in Germany?
Not bad. It's actually quite a peaceful country, so I have no complaint. The research opportunities are great, so yeah, nothing to complain about.
Wonderful. So I'm pretty sure that our audience is ready to listen to what Mr. Malinda has to say about his research these days and what he's up to. And I also heard that he has some very interesting stories to tell us about life in Germany. So, Mr. Malinda, the screen is all yours to talk to our audience.
Thank you. So I will share my screen, which probably you can see now. Yes? Can you see my screen?
Yes, we can.
Okay. So I will give a small introduction into what calorimeter is, what particle physics is in general, because in order to understand what I do, you have to understand what a calorimeter is. And so as an introduction, I will go into a little bit of details into what particle physics is in general. So thank you again for the introduction. And I will again go through these things a little bit before I get into the main topic. So yeah, I schooled at St. Peter's College, Colombo 4. Afterwards, I entered the University of Colombo and completed my bachelor's in engineering physics, as you mentioned, in 2017. And it was the same year that I actually started my master's in applied and engineering physics at the Technical University of Munich. And the reason for this is because I applied for my master's with pending results. So I didn't have my last semester results when I applied. And yeah, this is also something quite interesting for you if you would like to start your thesis or PhD or master's quite fairly quickly after your PhD or after your bachelor's. But yeah. So the structure of masters here in Germany is structured in such a way that the first year is all lectures, and then the second year we have to do a thesis, a 1 year long research. And I did my research at the Max Planck Institute for Physics in the topic of evaluation of scintillator tiles and silicon photomultipliers for highly granular graduators. I will explain what this is in the coming slides. Currently, I'm doing my PhD. I started this PhD in March, and I'm doing it at the institute called Deutsches Elektron- und Synchrotron, or DESY. So DESY is essentially a particle accelerator. It is the largest particle accelerator in Germany and the main one. So I am doing my PhD here, but as you know, institutes can't award PhDs. So therefore, I am also enrolled as a student at Heidelberg University. And my topic is fast readouts for highly granular CPM on tile calorimeters, but I'm actually specializing in the CMS experiment at CERN. Additionally, I also was a summer student at CERN in 2016, and my project at CERN was timing analysis of silicon diodes from CMS test beam data. And what is interesting about this is that this was essentially what I'm doing right now as a PhD student was essentially a continuation of this summer student project that I was doing. So yeah, it is like destiny just pushed me back into the same field that I fell into back in 2016. And yeah, for that opportunity also, I'm extremely grateful, and I got this opportunity because I was a student at University of Colombo, I believe. So yes, thank you again for having me, and thank you to the University of Colombo in general for giving me this privilege of experiencing research and research and everything that came with it. So yeah. So now I will go a little bit into the standard model. What is the standard model? And yes, so let's start. So yeah, back in the 1600s, people believed that the world was made with something called atoms. The smallest fundamental building block of the universe was called atoms. But then towards the 17th, 18th, 19th centuries, they found out that no, this is not the case. There are smaller particles inside called protons and neutrons and electrons. But then again, early in the 20th century, people again found out that no, this is also not true. There are particles that are even smaller than this in the universe. And this is the model of those particles, which is essentially the standard model of particle physics. So if you are in third year or fourth year, probably you know about these particles, but of course, if you're in first year, second year, you probably don't know. And if you're from a school or high school, then definitely you wouldn't. Oh, now I think it's in the syllabus, but mostly people top and bottom. Bottom is also called beauty in some countries. And then there are 6 leptons. There's the electron, muon, and tau. And then the 3 neutrinos, which are electron neutrino, muon neutrino, and tau neutrino. Apart from this, there are 4 fundamental forces: in the electromagnetic force, weak force, strong force, and the gravitational force. The gravitational force is not included in the particle physics standard model because it is extremely weak compared to the other 3 forces. So the 3 forces in the standard model are the electromagnetic force, and it has the force carrying particle, the photon that we know of. And then there is the weak force, which is the force that you see in radioactive decay. And the force carrying particles are W and Z bosons. And then we have the strong force, the gluons, and the force carrying particle called the gluons. And the strong force is essentially what keeps the neutrons and protons as they are, because these are the particles that dictates what's happening inside these non-fundamental particles, like the like the protons and neutrons. Apart from this, there's also the Higgs boson and the Higgs field. So the Higgs field is what is responsible for giving these particles its mass. So probably you all know what a particle collider is. So a particle collider, a particle accelerator is essentially it's essentially something like you accelerate particles such as electrons or protons. You accelerate it into extremely high velocities and then force it to collide inside particle detectors. So particle detectors, there are different types of particle detectors, especially in particle collider experiments. Usually there is this one type of common configuration that they use. And so I will be fixing onto this type of configuration mostly because my research is essentially linked to these types of particle detectors. So the particle detectors there, it's like a onion. It's completely layered. You can actually see it here. This is the CMS detector at CERN. So it looks like an onion. They actually even sometimes nickname it the cylindrical onion. Yeah. So this is comprised of different types of detectors. You have the inner tracker, which you can see here. So the inner tracker is essentially these layers and layers of trackers, where essentially if a particle collides and another particle is emitted, because of the magnetic field, it goes through these silicon trackers and moves in one direction. If it's a positive charge, it deflects in one direction, and if it's a negative charge, it deflects in the opposite direction. And then by taking the radius of these deflections, we can calculate the momentum of these particles and reconstruct the momentum of the particle. Afterwards, there's the calorimeters, which you have the electromagnetic calorimeter and the hadronic calorimeters. This is essentially the place that calculates the energy. So if a particle goes through this particle creates what is called a shower, which I will explain what is in the next slide. And this shower essentially deposits energy in the calorimeters, and this energy is then calculated to find what the energy of the particle was. And then finally we have the muon system, which is the largest part of the particle collider. And this is solely because the muon, which is a fundamental particle, this muon cannot be stopped in a particle experiment. It's a particle that has such a high momentum that it just leaves the detector system unharmed. And so in order to calculate the energy of these muons, we definitely need to calculate, we have to manage to find out what the energy is. And so what they do is they have these muon trackers, which is something like the inner tracker, where you again force it to deflect in a magnetic field, and then using the radius information, you can calculate the energy and the momentum of the muon. So yeah, this is the typical layer structure of a particle collider. So I told I will speak about showers. So this is how you essentially calculate the energy. So there are two types of showers. There's the electromagnetic shower and hadronic showers. So the electromagnetic showers are created by photons and electrons. So for an example, if you have a photon and then it goes through an absorber, which is essentially a material. So if it goes through a material and if the photon has a high energy, it will produce electron plus and electron minus, and this is called pair production. And so then afterwards, after this electron is produced, this electron also can then scintillate, or it can produce another photon when it passes through material. And this is called Bremsstrahlung, which is a German word for breaking radiation. So essentially electromagnetic showers comprises of only pair production and Bremsstrahlung, which means that an electromagnetic shower is completely made up of photons and electrons. A hadronic shower is much more complicated. A hadronic shower is created by a hadronic collision, like for an example, a neutron, and it collides with a nucleus in the absorber. And when it collides with the nucleus, we call it a spallation event, which essentially means that the nucleus just breaks apart. And it produces all these jargons of pions, neutrons, muons, and all whatnot. And it can also create photons and electrons, which will again then give an electromagnetic component. So then by measuring the energies of these individual particles, we can measure the energy of the initial particle that collided with or entered the absorber. So this is essentially what we try to do inside the calorimeter, which I am working on. In order to understand calorimeters in a little bit more details, I would like to introduce you to the two types of calorimeters. There are homogeneous calorimeters, which means that a single material it creates the shower that I mentioned earlier, and it does the energy measurements. So a single a single material is capable of doing both of these aspects. The sampling calorimeters are different. They have alternating materials. For one type of material that does the particle shower creation, and then another type of material that does the energy measurement. And yeah, so these are called sampling calorimeters, and I personally work with sampling calorimeters. Okay, so now I will go more into details of my thesis. So this is essentially the motivation for my thesis, my master thesis first. So the hadronic calorimeter, the problem with hadronic calorimeter is that because there is this hadronic component in the hadronic shower, it always gives the worst energy resolution in the detector system. And this is a big problem when it comes to big experiments where you need to see all the hadrons that are produced. And so what we have come up with as a solution is what we call particle flow. So this is essentially to limit the use of the hadronic calorimeter and give all of its functionalities to the other detectors. So for an example, the particle flow algorithms, what it tries to do is to limit the HCal and the ECal by giving its all of its information to the inner tracker. So for an example, if we have a charged particle like an electron or a proton, when it goes through the charge through the tracker, it will shift in a direction, and then we can get the momentum information from this, and then we can calculate the energy from this, and this is more accurate than the energy in the HCal. So if we do this, then we don't need to use the HCal for these type of particles. So we just essentially do everything there and then limit the use of the HCal. However, there are neutral hadrons also, and these neutral hadrons only can be measured in the HCal. And so the HCal is still important, but now it is less important than it was before. However, how modern particle physics experiments, how particle collider experiments run is that these HCals and ECals are made of long continuous layers. And so for an example, if an electron passes through one place and a photon, which is a neutral particle, passes through another place, since it is a one long huge block of material, we do not know which one is the electron and which one is the photon. And this is a problem. And so we need some sort of spatial resolution. We need to know exactly where the particle track is in order to associate the particle that is in the inner tracker to the particle that we measured in the ECal or the HCal, that's the electromagnetic calorimeter or the hadronic calorimeter. And so we need to break it into smaller pieces. And for this, what the CALIS collaboration has come up with, that is the collaboration I am part of. So the CALIS collaboration has introduced something called the CPM on-tile technology. And this is essentially what we do is we segment each layer into small spatial layers of 3 by 3 centimeter area. So this is essentially done by wrapping plastic scintillator tiles and placing it on top of silicon photomultipliers as shown here in the diagram here. And of course it's wrapped with reflective foil so that we can measure everything. So how these silicon photomultipliers work and scintillator tiles work, I will get to in the coming slides. This was such a successful idea that CMS, the CMS collaboration decided, that CERN CMS collaboration decided to use this technology in the upcoming upgrade of the Large Hadron Collider, the upgrade of the CMS. And this is essentially what I'm doing in my PhD. So yeah, my master work and my PhD work is extremely linked together. Yeah, so in my master's, what I concentrated is essentially what happens if the tile is not correctly positioned over the scintillator tile. So positioned over the silicon photomultiplier. So if it's not positioned correctly, how the performance will be impacted. So this is essentially what I did for my master's. So I will now go into details. So how I did this experiment was, here we have a strontium source, which is a radioactive source which emits electrons. And then we have a triggering scintillate CPM underneath. And then in the center, we have a wrapped tile placed over a silicon photomultiplier. And essentially, when these electrons pass through the tile, what happens is that it scintillates light. So a scintillator is a type of material that essentially can convert charged particles or charged energies or a charge into photons. And that is the specialty of scintillators. And then silicon photomultipliers, what it does is essentially counts number of photons that it detects. So these silicon photomultipliers are made up of an array, a large array of individual small pixels. Each pixel is a photosensitive diode. And so if a photon passes through it, it will give a signal out. So that is essentially how a silicon photomultiplier works. So for an example, if we have an electron passing through, the electron will scintillate photons, and those photons are then pushed towards the silicon photomultiplier, and then the silicon photomultiplier can read out how many photons were produced. And then what my thesis was to move the strontium source over the entire area of the wrapped tile, so that from each individual location on the tile, we can find out how many photons were produced and how it affects the performance if there is a misalignment in a direction. So yes, so this is again what I was explaining. So we have what a single photon emission would look like. So here we have a zoomed image on these silicon photomultipliers. These silicon photomultipliers are extremely small. It's I think the silicon photomultipliers that I used were 1.3 millimeters in the length, and it's a square. So that's 1.3 into 1.3. And yes, so here we see each individual diode in the silicon photomultiplier. And so if a photon passes through this, it will produce a signal as shown here. So then we have what the actual signal from the electrons look like. So the electron passes through and produces the photons, as you can see. And these photons tend to the reflective foil is reflected back onto the CPM. And then if we know the the values of the single pixel and then the values of the multiple pixels, then once we divide these two, we can find out how many photons were produced. So this is essentially what I was doing. And this is essentially a picture of my master thesis. This is essentially what I produced in order to get the results for my master thesis. So yeah, I constructed this, I wrote the code, and yes. Yeah, this I already showed. And now here what you see is essentially what I was explaining. This is what you see is how the misalignment affects the light yield. So each individual pixel you can see is a light yield measurement, or the number of photons that were produced when the source was on that position on top. And so we can essentially do a scan that way you can actually see what the scintillator looks like. It looks essentially like a photograph of the scintillator. And yeah, what is interesting is that when you make the misalignments in a certain direction, the patterns that are created on the scintillation changes, the light yield patterns changes. And so my thesis was essentially a measure of how well we need to keep the system aligned in order to have a very uniform, like this, a uniform light yield throughout the tile. Because this is essentially linked to where and when a particle goes. So essentially in a real experiment, if a particle goes through, okay, for an example, let's take this. A particle goes through somewhere here. We will measure a lesser energy than a particle that goes through here, which is a significant problem because then we have uncertainty in our measurements. And so we need to limit these sorts of configurations and try to keep it as least misaligned as possible. So my research was to see what is the percentage of misalignment that we could do and get away with having a reasonably good light yield. So for this, I made some calculations. This I'm not going to go into details because, of course, this is it can get a little bit of a heavy topic. So I just wanted to show you that we did this for different types of tiles and scintillators and CPMs, sorry. So these are for square scintillators, sorry. These are for square scintillators. These are for hexagonal scintillators, and these are for rhomboid scintillators. And yeah, we can do it for any amount of scintillators that we need, and for any type of scintillators we want, material, reflective foil, and so on. And this was essentially what I did for my master's. This is the highlight plot from all the results I got. Again, I'm not going to go into details because it's a bit of an advanced topic. However, what we observed is that as of course the misalignment increases, the light yield asymmetries increase, and it can be affected by the tile wrapping, tile material as observed. But what is most important is that we observe that this scales linearly, which is quite a nice, remarkable result, which means that if we reduce it to some extent, we can reduce the effects of this. And if you want to learn more about this, you can read my publication, which is linked here. Just have a Google search and you could find it. Now I come to my PhD. So I started my PhD in March, and so there's not much to report on that yet. However, I also have to tell you, these things is still under development, and so because of that, I can't share too much information on this. So I will give a small overview of what this is, and I hope that is okay. So yes, what I do now is essentially like a continuation of my master thesis. So essentially in my master thesis, I was working with CPMs and scintillator tiles, but now I have this electronic system that does CPM on tile readouts of entire layers like shown here. So essentially we can at once read out 64 or 72 amount of scintillator and CPM data at once every nanosecond or every 25 nanoseconds. And so this is essentially trying to scale what we did in my master's into a larger project so that it can be implemented in the CMS. So initially I told you that the technology that this Callis collaboration introduced will be used in the CMS project, and now I am actually involved in this project. So my idea, my work is essentially linked to trying to improve the electronic systems so that we will have proper good signals from all the scintillators and CPMs that we have, that we will be producing. And yes, this is really front edge research, and this readout electronic system is still the second prototype. There's going to be a third prototype, and then it will be produced for the CMS final experiment. So this is really still in development. It's still an ongoing process. And yeah, hopefully if everything works, this will be commissioned in the CMS experiment in 2026. So I will explain how we now do this experiment. I told you this is like a scaled up version of my master thesis, and it's because of this reason. So we have something called test beam facilities. So test beam facilities are large scale facilities where essentially you have a particle beam that is directed onto what where your detector is. So you keep the detector in front of, especially in DAISY, we have electron beams of 1 GeV to 6 GeV. So we keep our detector in front of a high energy electron beam so that it will just pass through our detector. And then from the electronic system, we try to read if the data we get is accurate or not. And so this is essentially how we test this. So we are now currently testing different CPMs, different tiles, and different materials, as well as the different types of reflective foil configurations. And yes, it's an ongoing process, and we also work on improving the readout systems and the software. So this is essentially the goal of my PhD. Here is what the test beam facility looks like, in case you are curious. So of course, even though it sounds quite brutal when I say that there's an electron beam that is coming out, these things are invisible. So you can't see the electron beam. So essentially the electron beam goes through all of these and then passes through this. So here now, of course, the electron beam is off because I am inside. If these are high radiation, high security facility, so you can't essentially just walk into it. So we have to take separate measures, we have to take a course in order to go there, and so on. So essentially what happens is, this is the detector that which I showed you earlier, and the electron beam just passes through this, and then we measure if everything works perfectly. Yes, so that is it from my master's and PhD work side. I hope you enjoyed that. And now I would like to show a little bit of my story here in Germany. Of course, it started in 2017 after my bachelor's. The convocation was in August, and then by October I was essentially here in Germany. So yeah, I started my academic journey at the Technical University of Munich. This is a very famous university if you have just checked it. This university is unique because it has these parabolic slides. If you have, of course, I'm sure you have seen countless beams of this because I have seen myself. So essentially, if you go to the 4th floor, you can just slide down to the ground floor in these slides, which is quite a nice experience, I must admit. So yeah, I studied here. This was where I did my master's. And I did my master thesis at the Max Planck Institute for Physics, which I took a photo in front of, which is here. And then this is from a very important milestone of my life. So as you know, in 2012, the Higgs boson, the discovery of the Higgs boson was announced by CERN. And this was done in this place. So this is in CERN, this is the main auditorium of CERN. And this was where that announcement was done. And I had the privilege of giving a talk on my master thesis here. And yes, so I consider that as a huge privilege, and that's why I added this picture here. And yeah, if I talk about the city of Munich, the Munich city is quite nice. It's a very Gothic city, as you can see here from the city center. This is called Marienplatz. And of course, if you are a football fan, you probably know the FC Bayern Munich stadium, which is the Allianz Arena. And I had the privilege of also going there in person to watch a match, which was quite an intense experience. Another thing about going to Germany or going to Europe, mainland Europe, I'm not talking about England or Northern Ireland, I'm talking about Europe, mainland Europe. The one good thing about going to Europe is also that you get to travel to 26 countries without any visa, because it's a Schengen visa. So I had the opportunity of going to many countries, including Austria, which I took a picture here. And then here, this is from Potsdam, which is a city close to Berlin. Now I live in Hamburg. I moved in March for my PhD. So DSC is in Hamburg, so therefore I had to move to Hamburg for my PhD. These are a few photos from Hamburg. This is what the city looks like. It's a very beautiful city. It's a city built on top of lakes, or in top of a river. Oh, I forgot the name of the river. Sorry, but it's built on top of a river, and it's a very beautiful city. And I really enjoy my time here in Hamburg. And yeah, on an ending note, I would like to show my research in a nutshell. So I work now for the CMS NCAP calorimeter group, where I work specifically on the highly granular calorimeters. And so when I visited CERN last year, I took a picture in front of the actual NCAP calorimeter. So this is quite another milestone in my life, I would say, that I stood in front of the detector that I'm working on, wearing a shirt that I actually also shows the CMS detector. Yeah, and on the right-hand side, this is the DESY Hera tunnel. So DESY is also quite an important experimental facility in all of particle physics, because it was at DESY that they discovered the gluon. So the first experimental evidence of the gluon came from DESY, and this is where I work now. So this is also for me a huge privilege. Yes, with that, I would like to end my talk. I hope you learned something, and I'm open for any questions that you may have. Thank you.
Thank you very much, Mr. Malinda, for that very educational talk about particle physics. I'm pretty sure most of our audience gained a lot of valuable insight into what this field is all about. However, our audience today is quite diverse. We have people ranging from school kids to to people who know a lot about physics. So, to cater to everyone, I'd like to remind them that this person that we have on screen today, who's doing cutting-edge research in the field of particle physics, was a school kid just like some of you. So, Mr. Malinda, I'd like to take you back to your school days. What exactly led you to this stream of science, and what were your school days like?
Okay, so in school, I was a bit of an introverted kid, of course. Actually, my science enthusiasm started even before school, because as a kid, I remember that this was when I was in school too, but I was in primary school, so I was like maybe 8 or 9 years old, and back then, I don't know if you remember, there used to be these columns in papers where they show these scientific astronomy related things. So there were about black holes, wormholes, and all these galaxies, supernova, all these things on papers, and I was interested in them a lot. And so what I did was I used to make paper cuttings and then have my own scrapbook comprised of all of these things. So this is essentially where my inspiration for physics started. But with time, of course, my ideas changed, and I wasn't sure what I wanted to do with life. Until around A-level time, I sort of like a relapse. I started back liking physics again. And yeah, when I did my A-levels, I had a pretty good idea that I wanted to be a physicist. And so it essentially led me to the University of Colombo. And from there onwards, I didn't know what type of physicist I wanted to be. And then everything changed in 2016 when I got selected to go to CERN. So this was essentially the point of no return for me, where I decided, okay, particle physics is super awesome, I'm going to stick with it. So yeah, that is essentially what happened. I also used to be an athlete, by the way, in school. So I wasn't exactly like a nerd. I was a big nerd, but not too much.
Very wonderful. So yes, as a person who came into science and came to the Faculty of Science, University of Colombo, I'm pretty sure you have some wonderful memories of your university life. You said you're not a nerd, so you definitely should have some wonderful memories. Can you name some of them?
Well, I think from the university life, my main memories are essentially the incredible people that I met. My batchmates, the seniors, the juniors that I communicated with. All of these things are, if someone asked me to mention a single memory, I would say it's more than the events. It's actually the people I met that is the most significant in my life. I still have contacts with them on a daily basis. So yeah, it was actually the most important thing for me. And of course, being part of the Physics Society was also a huge part in my life. Before physics, I also was part of Rotaract, which I enjoyed immensely. So in first year and second year, mainly, I was a Rotaractor in the university. And then when I joined the Physics Society, it was essentially Rotaracts on education. Because we are now, instead of doing, of course, we do public service and stuff like that, but also in the Physics Society, it's essentially popularizing physics. And this I resonated extremely a lot, because I was really passionate about physics and I wanted to share that. And so, the Physics Society, especially the physics talks that we did, I really have very fond memories of them. So, yes, I think these are the things that these are the memories that I have.
You indeed had some very wonderful memories then. Right. So, Mr. Malinda, did you have your path carved in stone? This is what I'm going to do from a very young age? Or were you someone who just went with the flow and decided on the spot?
I did not have a path in mind. Like I said, when I was a kid, I was interested in physics. I was actually more interested in astronomy. But as I grew up, of course, this is a little bit of a stupid comment to make, but when I was about 16 or 17, or maybe even smaller, I watched this documentary about how the moon landings were fake. And that really demotivated me. And that sort of sidetracked me from thinking that maybe astronomy is not for me. But of course, today I know that it wasn't faked. I can give you proof if you need. But yeah, that sort of pushed me from astronomy to these other fields of physics. And then when I started going to university, there was this lecture in the first year by Rosa sir, where he actually showed a particle physics experiment. He showed what CERN looks like in using an animation, and I really liked that. And then when I went to third year and I saw the applications, they're calling applications for CERN, I thought, okay, this is going to be a good opportunity. And I applied. And essentially, if it was that decision that forced me to take that, not forced, but it was that decision in my life that pushed me to think that this is the type of research that I want to do. So no, it was not carved in stones. It was all because of personal experiences.
That's indeed a good lesson for all our youngsters here. And yes, so a physicist needs to have certain skills, right?
Yeah.
What do you think are essential skills that a physics student should have to succeed in this field?
That's a very good question. The first thing that you need is, of course, a good physics education. So I can recommend University of Colombo for that because I got my education there. I'm sure all the other faculties and all the other universities also have this, I don't know. But as a person from the University of Colombo, Faculty of Science, Department of Physics, I can recommend this department with the bottom of my heart. And also, so yeah, apart from physics, I think the most important thing you can ever think of in terms of being in this field is coding, script language, learning to code. Of course, in the university we learn some of these languages. I think if you are part of the Department of Physics, you get to learn MATLAB and C programming to some extent, which is a very good idea. But I would also recommend learning Python because it is the up and coming language, and it's a very easy language. If you are a student of physics in third year or fourth year, then you would learn MATLAB, and if you know MATLAB, learning Python is very easy. And even if you don't know MATLAB, even if you don't know any coding languages, Python is a relatively easy language to learn. You can just look up all the tutorials online and then follow them and learn how to code. Because if I take my master thesis, everything was with Python. And if you take my PhD, right now again I'm doing in Python. And when I started this journey, I didn't know Python at all. And so it was like an extremely important wake-up call for me to learn a coding language. Thankfully, in my master's, my first year I had a lecture in Python, and because of that I learned to some extent what Python is and how Python works. But if a person wants to come into this field, I would recommend that you learn Python beforehand, but of course you can also learn it while you're doing it, like everything else. So yeah, coding language, physics, this is, I think, and of course presentation skills. You need to learn how to do a presentation properly. So, yes.
So among all of these skills, I'm pretty sure that another thing that we need to learn is how to properly plan something and execute it. I think that's very important in doing research. So what can you tell our audience about how to create a good plan, how to stay on it, and how to execute it?
Okay. So let me then take an example from a research project. So for an example, you got a research project in fourth year. Let's take that as an example because then we have a clear goal. So yeah, if you get a research project, now you have a clear goal. You know where you want to go and what you want to achieve. So then what you have to first do is make a work plan. So you tell to yourself, okay, for this amount of time, for the next month or so, I'm going to concentrate on this. So for an example, I want to learn the background of this experiment. So therefore, for the first month, I'm going to solely experience this. So 90% of my experimental time, I'm going to study what the background is. While doing that, you start slowly working your way into getting into that correct mindset. So for an example, if it's a coding project, a research project that involves coding, you start to write the basic skeleton of the code that you want to implement by the end in the first month while studying the field. So you have a logbook having a logbook is very important. Take a book, write down what you want to accomplish, write down what your work plan is, and then each day write what you accomplished and what you want to accomplish in the next coming week or next coming month, so that when you open the book on the following day, you have exactly everything written down. And likewise, slowly work up and make very unrealistic targets. So for an example, if you want to make a code about, I don't know what, something that is quite massive, you put the bulk of it into the first half of your year. And then you know you're never going to achieve it, but you have at least done most of the work by the point that you know that you can achieve it. So essentially, you are motivating yourself to do it rapidly, but also take your time and then do it properly. So once you have like the first everything figured out, then the rest just comes naturally. So this is essentially what I did.
That's quite good advice for all of our people who, like in my batch, who are about to start their research in a few months' time. Yes, so there are quite a few of our people who are worried about selecting, like applying for a special degree. I'm talking about our junior batches. Yes. So, like one of the biggest concerns that they have is, what are the opportunities we have after we do a special degree? What can you tell about that exactly? What are the opportunities that people have after doing a special degree? Especially for engineering physics people, because that's what I have written on the script here.
Yeah. So if you talk about, so each individual physics degree is different. So if you do a physics degree in physics, then it's different to a person who does the degree in engineering physics or computational physics. So if you do the degree in physics, of course, then you have a clear-cut path. You can easily get into any university that you need in physics. That is quite an advantage if you want to do physics special. And then if you want to go into engineering physics, also you have the same opportunities. Engineering physics is more catered towards electronics research. So if you want to be an electronic engineer or something like that, you can very well do that, because it caters to that area very well. And something that made me also enjoy engineering physics was that there were a few lectures that were directly involved with particle physics. For an example, I believe the lecture is called Instrumentation Physics, which is a very good background lecture if you want to go into experimental particle physics, because it covers all the basics. So all the stuff that I actually showed in my first few slides, except for the background with particle physics, it was essentially there in that lecture. So yeah, so if you want to go into something like what I'm doing, particle physics, engineering physics is also a very good way to start. And then we have computational physics, where computational physics is essentially mostly catered for to go into the field in computational side. So of course there are plenty of research opportunities also. And yeah, so each of these are unique. So it depends on you as a person. If you want to do what type of research you want to do, you have to make a decision which special degree you want to do. However, it does not mean that if you go into one type of physics degree and then want to go to another, you can't. It's not like the computational physics student can't go into physics to high energy physics or something like that. That is possible. So if you have the basic understanding of physics, if you have the basic knowledge of physics, if you have covered all the basic subjects in physics, then going to research is not a problem at all if you have a special degree. So this is, I think, the main takeaway message from this.
Yes. So, Mr. Malinda, we are running out of time. So, and I'm asked to give questions, like give an opportunity for our audience to ask questions. Please feel free to drop them in the group chat. While we wait for questions, I'll just ask a small personal type of a question. What do we need to do to get to university in Germany?
Well, of course you need to have a bachelor's. Afterwards, you just apply. I don't have any other explanation to give, because the fact that you already have a bachelor's is itself a big qualification. However, I must mention that unlike in US, In Europe, you need to have education is free in Germany, but still you need to have the living cost. So this was a big concern for me because I'm not a rich person. However, circumstances aligned with in such a way that I actually, however, managed to find the money that I need. So that is a big concern for a person who does not have money. But at the end of the day, the research in Europe is extremely good. That it is an opportunity that if you miss, it's a wasted opportunity, I would say. And yeah, so you need the proper qualifications, you need the recommendation letters. Of course, you need a motivation letter. So the motivation you have to specifically write to the university itself. You have to target the university. You have to compliment the university. And then you have to also explain why that specific program is good for you and why you want to actually do that specific program. And these are some of the key aspects. Even if you apply to US, no problem. These are the key aspects you have to cover in a motivation letter. And yeah, in general, after you come to Germany or come to Europe, I think in research terms, it's very easy. And Germany is a country known for a high amount of English speakers. So because of that, you don't need to know German to come to Germany. And the masters and PhDs, there are plenty that are in English. So you don't have to do your masters or PhD in German. And again, as I mentioned, if you come to any country in Europe for your PhD or masters, you get a Schengen visa, which means you can travel a lot. You can travel 26 countries, which is amazing, I would say. And yeah, so this is essentially how I essentially applied to Germany.
So yes, we have a question from our audience. Prince Tushar, would you like to ask it by unmuting yourself, or should I read it out for you? Okay, so I'll read it out. So Prince Tushar is asking us, what kind of jobs can we do while we are studying in Germany? And what kind of range of salary can we earn per month? And he's asking whether he can get the cost of living in Germany per month by said jobs.
Yeah, so there are varying jobs opportunities while doing a job while studying in Germany. Of course, there are visa restrictions that you have to take care of. So as a student, you can work for 20 hours per week, or in other words, 120 days full-time or 240 days part-time in a work environment. So you can earn for this amount of hours, a fixed amount of hours. And the amount of salaries that you get from this depends really on the type of job you get. If you work in the university, then sometimes they tend to give hours that are much less than what is required. So not required, sorry, what you are allowed. So for an example, I was working in an experimental institute called Max Planck Institute, as I mentioned. And at the Max Planck Institute, I got a salary, but I was only working 8 hours a month in a contract. So I was earning around 400 euros, 500 euros per month, which is not a lot. And yeah, so that is essentially, if you are in that type of job, how much you would get. However, if you go into the industry, you can earn much more than this. You would get contracts that are essentially 18 hours or 20 hours per week. And in this case, you can earn much more than that. Of course, there are tax limits, and then some of the money will get tax deducted. But you will earn enough that you can survive your entire stay in Germany if you get one of these jobs. The cost of living in Germany depends on the city. I was in Munich, and this is like the worst city you want to be in if you're concerned about money, because Munich is the most expensive city in Germany. And I had the privilege and disadvantage of living in Munich for 2 years of my life. But I managed to overcome it without actually having too much of a problem. So if I could do it, I'm sure you could too. So that's essentially what I can say.
Yes, I hope that answered your question. Do we have any more questions from our audience? If so, please Either you can raise your hand on the Zoom meeting, you can type it in the chat. Or if not, we can wrap things up. Okay, so I don't see any more questions coming. That brings us to the end of this wonderful session that we had with you. We are thankful to Mr. Malinda for sharing some of your time. We have an official vote of thanks that's coming up. And after that, we will be taking a photograph of with everyone having their videos on. So while you get ready for that, can I have Naduni Eratna, the Assistant Secretary of the Physics Society, to deliver the vote of thanks. Naduni, the screen is yours.
Thank you, Udita. I am Naduni Eratna, Assistant Secretary of Physics Society, University of Colombo. So it's a great privilege and honor to do the vote of thanks of this session. So my first and foremost gratitude goes to our keynote speaker, Mr. Malinda Shiram De Silva, for joining us and sharing his valuable thoughts and experiences with us. Moreover, our heartiest gratitude goes to Professor Balodaya, Senior Treasurer of the Physics Society, along with all the lecturers and demonstrators for their guidance and the support. Then I would like to thank Mr. Iran Kavinda, President of the Physics Society, along with all the committee members who supported us behind the screen. Then eventually I would like to thank all the participants for joining us, and we believe that you earned a lot from this session. Once again, big thank you for joining us. Thank you very much.